This video will discuss the uses of IR spectroscopy. The first thing we have to talk about is what is the form of an IR spectrum that is collected from those bond vibrations. For those of you who haven't seen one before, when we were talking about UV vis, we had something like absorption versus wavelength. And we had a peak, which seemed to make sense. Organic chemists, who like to do things backwards, instead of doing absorption, do the exact opposite of absorption, and IR spectra are typically rated as %T, not absorption. So when something absorbs, like this, that means that the %T goes down because less light is transmitted through it. So in an IR spectrum, peaks hang from the ceiling instead, sort of like a stalactite. So things that come down are the peaks. And instead of wavelength, we have wave number, which is that reciprocal centimeter, or 1/, wavelength that we had talked about before. This is not as unusual as you might think. The wave number unit actually is an energy, directly dependent upon energy. So it's energy proportional. So big numbers, like 4,000, is high energy. Little numbers, like 500, is low energy. This would make a lot more sense to me, except it's still numbered from low, now right to left, to high. So you kind of got to get used to the format of these IR spectra. Once you get used to the fact that peaks are hanging from the ceiling and the numbering system appears to be backwards, there is a lot of utility. Just like in UV vis, you can use Beer's law, but the real power of IR spectroscopy comes out at the specificity at which the bond vibration occurs. Remember that we said that the frequency is dependent upon the mass of the two atoms involved and the spring strength. That means that a C double bond O will have a different frequency than a C single bond O, and that gives us structural specificity. For example, this molecule has got both a C single bond O and a C double bond O. And those two different bonds having different masses show up at different frequencies. The CO bond approximately shows at 1200, and the C double bond O, because it has a double bond and it's stiffer, should be higher, and it is, always shows up at about 1700 reciprocal centimeters. Therefore, when we're looking at a spectrum, we can see a specific peak at 1700 reciprocal centimeters that tells us this molecule has a C double bond O and a peak around 1200, which shows us that it has a C single bond O. These very structurally specific peaks can be used to identify compounds' structure. One of the first things that we want to be able to structurally identify is, since we're working with hydrocarbons, what is the nature of that hydrocarbon backbone? Using organic nomenclature, if everything has single bonds, so you've got as many bonds around that carbon as you can and as many hydrogens, this is called saturated with hydrogens. And it is referred to as an alkane. The ANE ending says that it's all single bonds. That means that this molecule, in this particular case, hexane, with hydrogens all around it, will be made up of two bonds, a CH stretch and a CC single bond stretch. A CH stretch for a saturated system, that means for single bonds, shows up at 2900 reciprocal centimeters. A CC single bond shows up, well, roughly 1400 reciprocal centimeters. So if we look at the spectrum of an alkane, we would expect to see a 2900 peak for those single bond hydrogens, and peaks at about 1400 reciprocal centimeters, which correspond to the CC single bond. If we have double bonds or triple bonds, as in this molecule, it is no longer considered to be saturated. This is now unsaturated because we no longer have as many hydrogens on it as we can. In an unsaturated molecule, well, such as, an alkene, where the ENE ending means double bond, this particular molecule is going to have both single bonds that are saturated and a double bond. That means that this molecule will have carbon-hydrogen stretching that is saturated at 2900, but it'll also have carbon-hydrogens coming from things that are unsaturated, which make things stiffer, at about 3100. In addition, we'll have the CC single bond at 1400, and now a CC double bond, which is stiffer, so faster, at about 1600. Again, if we look at this, we can see all of these components. We can see the CC double bond at about 1600, the CC single bond at about 1400. Now that peak starts to come over, so we have both 3100 and 2900. Although this may be difficult to see at this point, its indication is the fact that there is a peak here, which means there's probably a peak there. The last example would be where we have a triple bond in the system. If you have a triple bond, this is called alkyne, where the YNE ending means triple bond. Alkane, single bonds. Alkene, double bonds. And alkyne, triple bonds. This molecule has unsaturated, a CC triple bond. This is still 2900 and 3100. This one is going to be the fastest because it now has a triple bond, and this one will still be about 1400. This sharp peak at 2200 reciprocal centimeters can only mean it has a triple bond. Any molecule that has a triple bond can be specified by that particular peak. We have the CH stretches, and we have the CC single bond. So highlighting it, IR spectroscopy can be used as structurally specific information. The frequencies of these peaks are specific to the functional group of the molecule itself. So every single molecule will have a unique IR spectrum.